Hi guys, welcome to a new video on optimization under math studies. This video shall tackle further challenging questions, and we shall focus in this video on questions that have cylindrical objects. I shall tackle the two questions on the screen in front of you, and I shall begin question 1 shortly. So question 1 came in paper 2 May 2010, time zone 2, question 5. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So you are told that there is a dog food manufacturer that wants to cut production costs. She wishes to use as little aluminum as possible in the construction of cylindrical cans. In the following diagram, h represents the height of the can in centimeters and x the radius of the base of the can in centimeters. The volume of the dog food cans is 600 centimeters cubed. Show that h equals 600 over pi x squared. So in this first question we are required to find an expression for h given the fact that the volume is 600, and we can see that it shall feature in our answer. So the volume is given by pi r squared h. This is the volume of a cylinder, and here the radius is called x, so the volume shall be pi x squared h. Hence 600 shall equal pi x squared h, and if we want h to be alone, we just transfer the pi x squared to the denominator of the 600, and we get this red expression that is equivalent to the one provided in the question. In BI, we are required to find an expression for the curved surface area of the can in terms of x. So the curved surface area is equal to the area of the curved part of the cylinder, so the circular side part of the cylinder, ignoring the top circle and the bottom circle. We just want the curved part of the cylinder. So in order to find this area, I should conceptualize or visualize trying to paint this area. So I'm going to paint the curved part of the cylinder as per these lines right there. I'm going to color this part of the cylinder right there all the way around. So this part is given by the perimeter of the circle, the perimeter of one of the circles, either the top or the bottom, multiplied by the height. So the area of the curved part of the cylinder is equal to the perimeter of the base multiplied by the height, which is 2 pi r times h, or rather 2 pi x times h. So since the curved surface area equals 2 pi x times h, we shall just substitute this expression instead of h, getting 2 pi x times 600 over pi x squared, which simplifies to 1200 over x. Now in order to reach this simplest form, I have simply crossed out this pi right there with the pi in the denominator, and I've also crossed out this x with one of the x's in the denominator, so I am left with 2 times 600, which gives me 1200, and I'm also left with 1x in the denominator. Hence this final expression. Next, I'm required to write down an expression for A, which is the total surface area of the can, also in terms of x. Now the total surface area is equal to the curved surface area added to the area of the ceiling or the top and the area of the bottom. So I already have an expression for the curved surface area through I just need to add the area of the top and the bottom. So the curved area has already been obtained as 1200 over x, which I've placed right there. and I've added to that the area of the top, which is a circle of radius x, so pi x squared, and similarly the area of the bottom, which is pi x squared. Hence my final expression is the one right there in gold, 1200 over x plus 2 pi x squared. Next, in question C, I'm required to differentiate a in terms of x. So there is my expression for a. I have simply rewritten it, just transferring the x from the denominator to x power negative 1 in the numerator. This can help me differentiate, and a dash shall be as follows: negative 1200 x to the power of negative 2 plus 4 pi x. So this blue expression is the derivative of the red expression, which is almost the same as the gold expression, except for this x right there, which, as I've explained, I've transferred from the denominator to the numerator. Next, I'm required to find the value of x that makes a minimum, and the value of x that minimizes a is found by setting a dash to 0. So if a dash equals 0, I can find x, and this value of x is the value that minimizes the a. So what we've done here is we've set this expression right there to 0, and I've undone what I've done in the previous question, meaning that instead of x power negative 2, I now have x power 2 in the denominator. This can help me solve manually if I would like. Otherwise, you can sketch on the GDC and try to find the x-intercepts or the zeros of the function. However, for simple equations, I recommend that you try to solve manually, because sometimes sketching creates problems with the window and so on, and you waste a lot of time trying to get the sketch correctly drawn on your GDC. So this can easily be done manually, and let's see how to do that. So negative 1200 over x squared plus 4 pi x equals 0. I'm just going to take this negative expression to the right hand side and change the sign. So 4 pi x equals 1200 over x squared. I'm going to take this x squared from the denominator to the numerator on the other side. I'm going to multiply by x squared, so I get 4 pi x cubed on the left and 1200 on the right. Next, in order to isolate the x, I'm going to take the 4 pi right there and place it in the denominator. Finally, I'm going to evaluate this number on my GDC and get the cubic root, obtaining 4.57 for x. So this is the value of x that minimizes the area. Finally, I'm required to calculate the minimum total surface area of the dog food can, and this is simply found by plugging the value of x that I've obtained into the expression for a that I have also previously obtained in order to find the minimum area. So I'm just going to take the 4.57 and plug it into the gold expression right there instead of each of the x's, and evaluate this on my GDC, obtaining a final answer of 394. So take a minute to copy this down if you will, and I shall begin the next question shortly. So the second question came in paper 2, May 2014, time zone 1, question 6. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So we are told that a lobster trap is made in the shape of half a cylinder. It is constructed from a steel frame with netting pulled tightly around it. The steel frame consists of a rectangular base, 2 semicircular ends, and 2 further support rods as shown in the following diagram. So to explain this a little bit, there is my rectangular base, there is the length, there is the width, there is the opposite length, and there is the opposite width. So there is my rectangle. These are 4 of the rods. and we have two semicircular ends right there and right there. And finally we have two support rods which are right there and right there. So these are the rods that I have in my steel frame. So again, this is a frame, this is not a solid object, this is like a cage or something, and these are the steel bars used to construct this frame. So in question A, I'm required to write down an expression for t in terms of r, l and pi. So let's take a look at these variables. We are told that t is the total length of steel used in the frame of the lobster trap, and r is the radius of the semicircular end, and L is the length of the support rod, knowing that the support rods all have the same length. So if this is L, then this is also L, and this is also L, and this finally is also L. So in order to write down an expression for T, which is the total length of steel, I need to add up the rods together along with the semicircular ends. So I have L plus L plus L plus L. There are my four rods, and I have two semicircles, each of perimeter pi r, because this is half of a circle. So half of a circle has a perimeter of pi r. So each of the semicircular ends uses pi r of steel. So the length of steel, or the amount of steel used, the length of steel used to construct the semicircle is half the perimeter of a circle, which is pi r. So I have 4L, and I have pi r for the first semicircle, and I have another pi r for the second semicircle. But bear in mind that the perimeter of the semicircle shall give me this part, the circular part. However, I also need to take into account the diameter of the semicircle. This is not accounted for in the perimeter of the circle. So I'm going to have to add 2r for each of the semicircles to account for the diameter of each of them. Hence, in order to calculate the total amount of steel, as we said, I have 4 of the L's as well as the perimeters of the semicircles, and finally the diameters of the semicircles. And I need to add up all of these together in order to obtain an expression for T. Hence, T is equivalent to this green expression right there, 4L plus 4R plus 2 pi R. Next, we need to write an equation for the volume of the lobster trap in terms of R, L and pi, given that the volume is 0.75. Now this is half a cylinder, and the volume of a cylinder is pi r squared multiplied by the height. So in this case it would be pi r squared L, and since this is only half of a cylinder, hence the volume is pi r squared L over 2. In C, I'm required to show that T equals this expression right there. So let's take a look at how to obtain this expression. So as we mentioned, the volume is half of a cylinder, so pi r squared L over 2. I want to obtain an expression for T in terms of R only. I need to eliminate the L from the equation of T. I need to get rid of this L right there from the equation of T, and in order to do so, I shall use this second equation right there to isolate the L and hence eliminate it. So let's take a look at how to do that. I'm going to isolate the L in this purple expression for volume, and this is what I get. I get 2V equals pi r squared L, and then I divide by pi r squared on both sides, obtaining this expression for L right there. Now, since we know that the volume is equal to 0.75, I can replace this V with 0.75, obtaining this final expression for L in terms of R. Now what I'm going to do is I'm going to go back to the green expression and substitute L for 1.5 over pi r squared. And this should give me an expression for T in terms of R. So if we take a look at this green expression, I've rewritten it here in purple. So the only difference is that instead of this L, I've inserted 1.5 over pi r squared. And also, since I have R here and there, I can take this out as a common factor. So there is my R, and what remains is 4 plus 2 pi. So I've just taken out an R from these last two terms, and I've factorized, obtaining this expression right there, R times 4 plus 2 pi. Next, I'm going to simplify a little bit. So 4 times 1.5 gives me 6 over pi r squared, and this second term remains as is. This expression in gold is equivalent to the expression required in the question. Next, I'm required to find an expression for dt by dr, which is obtained by differentiating this expression right there. And also note that even if you do not manage to reach this expression, you can always use it to solve the rest of the question, D and E and F and G. So there is no reason why you cannot continue with the question if C is too difficult to derive. So our task is to differentiate this gold expression right there. I'm going to begin by taking the r squared from the denominator and placing it in the numerator as r to the power of negative 2. This will help me in my differentiation. So the derivative of this green expression is obtained in the red expression right there. So 6 over pi times r to the power of negative 2 becomes negative 2 6 over pi r to the power of negative 3. I've multiplied by the old power and I've reduced the power by 1. Next, for the second term, I have r multiplied by a constant. So this is like 5r, for example. 5r differentiates to 5. Similarly, r times 4 plus 2 pi shall differentiate to 4 plus 2 pi. So instead of r times 4 plus 2 pi, I just have 4 plus 2 pi. Now I've done some simplification here. I've only multiplied the negative 2 by 6, obtaining negative 12. This is the only difference between the red expression and the blue expression. So next, in E, we are required to show that the value of R for which T is a minimum is 0.719, correct to 3 significant figures. And of course, you should know that the value of R that minimizes T is obtained by setting T dash to 0. So I'm just going to go back to this expression right there and set it to 0 and find the value of R. Let's see how to do that. So there is my expression for T dash. I'm going to set that to 0 and I'm going to show you how to use the equation solver on your GDC to solve this equation. So in order to obtain this screen, I'm just going to press on math and I'm going to scroll up to the bottommost function, which is solver. I'm going to get this screen right there, and what I'm going to do next is I'm going to type in this equation in gold and attempt to solve it. So there is my equation. I've typed it onto my GDC and then I'm going to press enter. I'm required by the calculator to provide a guess as to what I expect my value to be. So let's just type in anything. Let's type 3 for example, and I'm going to press on alpha and solve. And the calculator tells me that the value of x is 0.7188, which is approximately equal to 0.719. So since this is a show that question, you are required to copy the entire figure from your GDC and then to show that this approximates to 0.179. So this number right there is very important in this question because it is a show that question and you get credit for showing that you derived the final answer from this number. So this is the more important number. You do not get any marks for this number because it was already provided in the question. Moving on, I'm required in F to calculate the value of L for which T is a minimum. So in order to find the value of L, I shall simply plug the value of R into the expression of L. So since L equals 1.5 over pi r squared, I'm just going to plug 0.179 into this expression right there, getting 0.924. Finally, I'm required to calculate the minimum value of T, and again I shall simply plug R into the expression for T, which is provided right there in the question. So I've rewritten the expression for T right there, it's exactly the same, and I've plugged the value of R into this R and this R right there. So there is my value, and on the GDC you can easily compute this and your answer is 11.1. So this concludes our question and this video. Take a minute to write this down if you will, and I hope you have found this useful.